This video will provide a walkthrough on how to balance an assembly line consisting of 11 tasks using the longest processing time first rule. Here's a precedence diagram for the problem, and you can see the 11 tasks we have to work with. The requirement is to balance the assembly line under two alternative output levels, A, a shift output of 40 pieces, and B, a shift output of 20 pieces. We're also to assume an 8-hour shift and use the rule choose the assignable task with the longest processing time. We're also asked to compute the efficiency of the line for each case. So let's get started with requirement A. In order to balance an assembly line, we first need to know the cycle time to determine how many tasks can be combined into a workstation. The cycle time, or CT, can be calculated as A divided by R, where A is the available time in a shift and R is the total required demand. For a shift output of 40 pieces, CT is equal to 8 hours times 60 minutes per hour divided by 40 pieces per shift. That results in 480 minutes per shift divided by 40 pieces per shift, or 12 minutes per unit, and that's the longest time a workstation can have. Next, we start balancing the line using the longest processing time rule. For station 1, we start on the left with the longest processing time, that's A. Then we look to add as many tasks as we can from longest to shortest time without exceeding the cycle time of 12 minutes. We can add tasks E and B with times of 4 minutes and 3 minutes respectively to make a workstation with a time of 12 minutes and 0 minutes idle time. The idle time is calculated as the cycle time minus the workstation time. So 12-minute cycle time minus 12-minute workstation time is 0 minutes idle. Next, on to workstation 2. Of the remaining tasks closest to where we finish, there's task G with a time of 7 minutes. We can then add tasks C and D with times of 2 minutes and 1 minute respectively. This results in a workstation with a total time of 10 minutes and 2 minutes of idle time, which is 12-minute cycle time less the 10-minute station time to make 2 minutes. Now on to station 3. Of the remaining tasks closest to where we finished, there's task F with a time of 6 minutes. We then look for a task with the next largest time, which is task I. Task I also takes 6 minutes. This results in a workstation time with 2 tasks and a total time of 12 minutes with 0 idle time. Now you see we still have ungrouped tasks, so we keep going. For workstation 4, the longest time is task H at 5 minutes. To fill out the workstation, we can add tasks J and K with times of 4 minutes and 3 minutes respectively to create a workstation with 12 minutes and 0 minutes idle time. Now the line's balanced. And then now we can add up the total workstation times to get a total of 46 minutes and a total idle time of 2 minutes. Finally, we can calculate the efficiency by taking the total workstation time divided by the number of workstations times the cycle time. 46 minutes divided by 4 workstations at 12 minutes each is 46 minutes divided by 48 minutes, and that equals 0.958 or 95.8% efficiency, which is pretty darn good. That also means the line is 4.2% idle, which can be calculated as the idle time of 2 minutes divided by the cycle time. Now let's see what a balanced line looks like with demand or shift output of 20 pieces per shift. First, we recalculate the new cycle time. The same 480 minutes is available on an 8-hour shift, but now we divide by the required 20 pieces per shift, giving us a cycle time of 24 minutes. And now we start balancing the line. We start station 1 with task A, and then start adding additional tasks with the longest time first until we get as close to 24 without going over. We add in tasks F, E, B, C, and D to create a workstation with 6 tasks and a station time of 21 minutes with 3 minutes idle time. Again, that's 24 minutes cycle time minus a 21-minute station time. Next, we move on to station 2. This starts with task G at 7 minutes, and then we add in tasks I, H, and J with times of 6 minutes, 5 minutes, and 4 minutes respectively. This results in a workstation with 4 tasks and a station time of 22 minutes with 2 minutes of idle time. Now, as you can see, we're left with one task, K, which, unfortunately, must form a workstation of its own. There are no more tasks, so workstation 3 contains one task for a total station time of 3 minutes and 21 minutes of idle time. Now we're done balancing the line. The total station time for this line with 3 workstations is 46 minutes, the same as the previous line. But in this case, the idle time is 26 minutes. This results in efficiency of 63.9%. Calculated as the 46 minutes of total station time divided by 3 workstations times 24 minutes cycle time. Students tend to assume that assembly lines with fewer workstations are almost always most efficient. This problem shows that that's not always the case, but it depends on what the demand is. Our conclusion here is that, based on the decision rule employed, longest time first, the line with the higher demand of 40 pieces per shift results in lower cycle time of 12 minutes, which necessitated more workstations, but resulted in a very efficient assembly line at 95.8%. Different decision rules may yield different results. This problem illustrated how important cycle time is to high efficiency when balancing assembly lines. The higher the required production, or R in the cycle time formula, the lower the cycle time, and, as we saw here, lower cycle time helps increase assembly line efficiency. Generally speaking, when balancing assembly lines, higher demand results in a lower cycle time and higher efficiency. Conversely, lower demand, and therefore required production, results in lower utilization of the productive resources, creating more idle time despite fewer workstations.